here's another problem on conservation of mechanical energy, and it says we're going to be going from gravitational potential energy into elastic potential energy, but actually there will also be some initial kinetic energy at the beginning. So here's the problem. It says that we have a 1.5 kilogram ball, which is thrown down toward a vertical spring at a speed of 2.6 meters per second. The ball is initially 3.8 meters above the spring. Once the ball strikes the spring compresses a distance of 12 centimeters. Find the spring constant of the spring. Well, let's draw our picture. In each of these problems, the first step is to draw the two moments of time that we're going to evaluate. And then we add in, the second step is to add in all the different types of energy which are present for each of the two situations, each of the two moments. So here's the first moment in time. It's when the ball is first being thrown down. So we choose that moment because we have information about the ball at that point. So the information that we have is, well, here's our spring, there's the ball. We know that the ball is initially a height of where? How high? It's 3.8 meters above the spring. I have a feeling this is going to be a big spring constant. And we know the mass of the ball. The mass is 1.5 kilograms. That's pretty big for a ball. And there's our 1.5 kilograms. And we know that the ball is moving at 2.6 meters per second at this moment. So let's write in V equals 2.6 meters per second. All right. At this moment, we are going to have some energy. We will have gravitational potential because of this height. So there will be mgh. And the other energy we'll have, that's an h. The other energy we'll have is kinetic, which is 1/2 mv squared. The spring doesn't have any energy at this point because it's not compressed. It's still relaxed. So there's no compression, there's no x. Thus, there's no elastic potential energy, no spring energy. So that's it. Those two are the only energies we have. Then this ball, it goes flying down, hits the spring, compresses the spring, and that's the second moment that we're going to evaluate. And the reason we choose that moment is because we have information about that moment. We know how far compressed the spring becomes. So let's draw that moment. Here, I'll do it over here. We've got this compression, and there, that's our spring, and right on top of it is the ball. Okay, now at this moment, the ball has impacted the spring, and then it's pushed the spring down, and in the process, it has slowed down until it eventually comes to a stop right here. That's the idea. So there's no velocity of the ball at this moment here. Instead, so that means, what does that mean? That means there's not any, there's no kinetic energy at all. Ke is 0, because the velocity is 0. So the kinetic energy is 0, and we have to evaluate whether there's any potential energy. Now here's what I would recommend. Wherever the ball is at this moment, let that be our 0 position. That's where the height is at 0. Okay? So I'm going to take that off. In other words, we are using this as our 0 position so that we can set the final potential energy, the final gravitational potential energy, to 0. So let's write that in. PEG is 0 here because of where we choose our 0 level. Good. Now, the last kind of energy that we know we have at this moment is the elastic energy, the spring energy. So that's PELA for elastic. And the reason we don't just use PEEL or PEE for elastic is because later in the year we're going to learn about electric potential energy, and that will be ELE. So we have to distinguish elastic from electric. Just a fun fact. Okay, we've got our initial energies, that's these two. We've got our final energies, that's just this. We write down our conservation of energy equation. The left side is where we add up all of the initial energies. The right side is where we add up the final energies. And let's just clear that up a little bit. So initially, MEI equals MEF. Okay, that's an E. Initially, there is mgh. We wrote that one down. And there's 1/2 mv squared. At the end, all we have is the 1/2 kx squared. Okay, the masses don't cancel, right? The masses usually don't cancel whenever there's elastic potential energy because there's no m in that equation. So now what we're trying to find is k, the spring constant. So you just plug everything in. Right? We have mass is 1.5 times 9.81. Now the height, this is tricky. At the very beginning, right, over here, you might think that the height is just 3.8. But we haven't taken this, right? We haven't taken this as our 0 level. We've taken down here as the 0 level. So the initial height of the ball has to be measured from this dotted red line, which is 3.8 plus the amount that the spring compresses to get down to this dotted line. So it's 3.8 plus 12 centimeters, right? And what does that come to? Well, 12 centimeters is 0.12. So this is 3.92. Then we have to add mv squared, 1/2 mv squared. The mass is 1.5. Velocity is 2.6. And because I'm out of room, I will say equals, and I'll put the rest of this over on the second line. Again, we have our x, which is 0.12. Remember, you must always plug in the distance here, the compression or the stretch distance. You must always plug it in with meters rather than centimeters. Just like we always plug in kilograms right here for mass rather than grams. Right? Mass is the only thing that gets a prefix. You put in kilo only for the mass, only for kilograms. Everything else has no prefix. So you solve for k, and it's not so hard from here. Right? You just calculate everything on the left side, then you multiply it all by 2 to get rid of the 1/2. 2 times all that. And then you have to multiply everything by, you have to divide this whole right side. So this is everything getting multiplied by 2. Then you have to divide everything on that side by 0.12 squared. And we're dividing this by 0.12 squared. Okay, let's see what our calculator says. And wow, you plug it in, and this is a big value. I am getting 8715.6 repeating. So with sig figs, we just make it 8700 newtons per meter. What a big spring constant. Yeah, it had to be something big because it didn't compress very much, and it had tons of energy. Right, 3.8 meters, that's a big distance. And 2.6 meters per second for a 1.5 kilogram ball, that's a big kinetic energy. So yeah, it had to be something big. That's what we expect, and there it is. That's what we get.